Hey guys, this particular problem is going to be dedicated to solving the problem we attempted previously. And as a brief recap on what we've done so far, essentially we've shown that our first block, M1, which for simplicity in this video I'm going to call MA, right, is in fact moving up the hill, right? And we managed to show that by showing that the tension force in this rope is enough to overcome the friction force and the components of gravity moving down the hill. Right? And consequently, that also implied that our second block, which I'll call block B, right, is also moving vertically downwards. And also for the sake of generalizing our solution, instead of calling this distance here 2 meters, even though it is 2 meters, I'm going to call it a distance h. Right? And that should be vertical. That should be vertical right there. Alright, well, not only does it mean that this block is moving down a distance h, but that also means that this block just here is moving up the hill a distance h as well, right? That means that this distance here is going to be a distance h as well. And also, and this should really satisfy your intuition here, that the magnitude of our velocity of our second block, block B, at any time is going to be equal to the magnitude of our velocity at block A, right? And that's because they're connected by this rope. If you can imagine it, just imagine playing with this block, moving this block down and moving this block left or right, assuming that the rope doesn't go slack. The velocity of block A will at all times equal the velocity of block B. And this will be important in this problem too. Alright, well, let's get started without further ado. Okay, well, let's recall what is our mechanical energy formula. Well, it's our change in mechanical energy of our system is going to be equal to the work done by all non-conservative forces. The work done by all non-conservative forces. And this just begs the question, what are the non-conservative forces acting on our particular system? Well, let's see. We've got quite a few. In fact, we've got 3. We've got a force due to friction, which is a non-conservative force, right, which I'll just draw here. We've got the force due to friction acting down the hill, which is a non-conservative force, and it will be mu kn. It's mu k because the object is in motion, and we know that, right? So we're concerning ourselves with the coefficient of kinetic friction, right? And we've also got our normal force as another non-conservative force too. So these are 2 non-conservative forces right here. And we're about to evaluate the work that they do. So that's our normal force N, and this is our friction force, mu Kn. But that's not the only one. We've also got a non-conservative force here, right? And this is the kind of reactionary force that the pin is supplying to keep this rope where it is, right? I mean, if you imagine it like, imagine the stress this pin is under, there must be a reactionary force caused by the pin pushing this rope to keep it where it is, right? So let's consider the work done by all of these 3 non-conservative forces. Well, we've got the work done by friction, right? What is the work done by friction? Well, it'll be the magnitude of our force due to friction multiplied by the distance the block has moved in the direction of our force. Right? So it's going to be the magnitude of our force, mu kn, times by the displacement our block has moved in the direction of our force, right? But notice, our block is not moving down the hill, and notice that our friction force is down the hill. Our block is moving up the hill, so it'll be multiplied by negative h, right? Negative h. Because they're in opposite directions. The force and the displacement are in opposite directions, so this will be negative. Alright, well, we've also got our work done by our normal force, which I'll call work normal, right? And notice that this will be equal to 0, because it's going to be our normal force times by the displacement our block has moved in the direction of our normal force. But since our normal force is always perpendicular to our path, and the block is assumedly staying on the path, that means that it's going to be our normal force times by 0, because the block isn't moving in the direction of our normal path, isn't moving in the direction of our normal force. It's moving perpendicular to it. Alright, What about our work done by our pin? What about our work done by our pin? Well, it's going to be whatever our reactionary force is multiplied by the displacement that the rope is having under the action of that force. But because the pin is staying where it is, and because the rope is also staying where it is, that means you're going to have whatever the force is multiplied by 0, which is 0. Right? As a result, the sum of these three works is going to be equal to our total work done by our non-conservative forces. Consequently, we're going to be left with minus mu k n times by minus h, right, plus 0, but I won't bother writing that out. Alright, well now we're in a good position to start solving for the left-hand side of our equation. And remember, the left-hand side is our change of mechanical energy of our system, right? And within our system, we've got two blocks, one of mass A and one of mass B, meaning that we need to concern ourselves with the change in mechanical energy of our first block plus the change in mechanical energy of our second block, right? So in other words, on our left-hand side, we'll be left with the change in total mechanical energy of our system will be equal to the change in mechanical energy of our first block, which I'll call block A, plus the change in mechanical energy of our second block, which I'll call block B, right? And that's going to be equal to our right-hand side, which is just going to be minus mu k nh. I just realized I put two negatives in there. There should have only been one. I'll just get rid of that. All right. Consequently, now we can re-express we can express the change in mechanical energy of block A as simply the change in kinetic energy, of block A, plus the change in potential energy of block A, and that's that's this term right here. That's this term. Right? And for the other term, it's going to be equal to the change in kinetic energy of block B, plus the change in potential energy of block B as well. And that's this term right here. Fantastic. And that's just going to be equal to our right-hand side, which is minus mu k n h. Right? Well, before I end this video, and I'm going to do 3 parts because I think 2 parts is just a little bit too long, let's see if we can figure out what our normal force is. Well, once again, let's resort back to our free body diagram. And I've done it before, but I'll do it again just quickly. This is our block right here on our slope. Take a good look. Essentially, we're going to have a whole bunch of forces acting on it. We're going to have our tension force, which I've drawn right here, our normal force, our friction force, and our force due to gravity. So let me redraw that below. Just as more of a minor recap than anything else. This is our block here on a slope, and it's going to have a whole bunch of forces acting on it mid-flight. It's going to have gravity acting down, it's going to have the normal force acting up, it's going to have our tension force acting to the right, and it's going to have our friction force acting down the hill. Alright, well, what is our normal force? And in order to figure out our normal force, we need to once again, and this shouldn't be a surprise, I did this in our first part, but I'm just doing it again, just more as a recap. To figure out our normal force, remember this is our normal force, and this is our gravity force, MAG, right? In order to figure out our normal force, we need to figure out the component of gravity in our normal direction. Right? So this is our normal direction right here, and this is our tangential direction right here, right? In order to figure out what n is, I'm simply going to take the sum of forces in the normal direction are going to be equal to 0, right? And notice that this is true regardless of whether this block is stationary or whether it's moving up the hill. And this is important, right? This is true regardless of whether the block is moving or not. Because if you think about it, the block isn't flying off the hill at any point. It's remaining stuck to the side of the hill and it's sliding up it, right? Consequently, the block isn't like going into the hill or it's not flying off the hill, so it's not going to be accelerating away from the hill at all. Consequently, this will always be true, right? And as a result, we can write that our normal force is going to be equal to our components of gravity in our normal direction, this beast right here. Well, we've done this before. We know that we can re-express this as, actually let me just do it. We know that this angle right here is going to be theta, meaning that this is 90 minus theta, which implies that this angle right here is going to be equal to theta, showing us then that this angle here is going to be equal to MAG cosine theta. Alright, I hope that makes sense, guys. That's our normal force, and that will always be our normal force in this particular problem. Alright, consequently we can write this as minus mu k MAG cosine theta h. Alright, and let's see if we can express the left-hand side out a little bit more. Well, the change in our kinetic energy of block A will just be a half times by the mass of our block MA times by our velocity of our block at our second point. Sorry, I should say the magnitude of our block at our second point. And I'll just write 2A, right? Squared minus V1A squared plus MAG, this is our potential energy. Notice that elastic energy is not involved in this problem, times by our change in height, Y2A minus Y1A, plus our change in kinetic energy of our second block, B. That's going to be a half MB times by V2B squared minus V1B squared. Alright, and that's going to be added to MBG, which is, then this is our gravitational potential energy right here, times by Y2B minus Y1B. Right? I've essentially applied the, I've essentially expanded this out to be equal to all of this. Right? And I've done the same for the other term right there. Alright, now, and of course this is going to be equal to our right-hand side, but I don't have space, so I'll just write it over here. It's going to be minus mu k MA GH cosine theta. Okay, well, I'm probably going to end the video really soon because I don't want to do the whole maths in one particular video, but essentially let's see if we can simplify this expression out a little bit. Well, we know that our velocity, as I discussed before, of our block A at any point is going to be the velocity of our point B, right? So this subscript is unnecessary, right? I mean, the blocks have the same magnitude of velocity, so it's pointless naming them VA or VB. I could instead label them V1 and V2, denoting the magnitude of our velocities at their certain points. Okay, I'm going to end the video here, just in the wake of a whole bunch of upcoming mathematics, and in the next video I'm going to solve this particular type of beast. Alright, bear with me.